Good morning, good afternoon, good evening, wherever you may be in this part of the world. Welcome to another session of my presentation. And this time, my presentation title is different types of testing that can be performed on a power transformer. My name is John Kweku Amooto, and I'm a professional electrical engineer for about 30 years, and I'm based in the United States of America. Next slide, basically, I'll talk about the outline of my presentation, and the first item is power transformer action, and where basically I'll give you a theoretical background of how a power transformer works. Next is definition and functions of the different components of a power transformer. Next is engineering standards and IEEE standards that govern a power transformer. Next is the routine test as part of the factory acceptance testing that is performed in the factory, and also design or type test as part of the factory acceptance testing. Design or type test usually is done when a new design of a power transformer comes into play. That is when the manufacturer has to prove beyond reasonable doubt that the design of the new transformer is going to work as it is supposed to design. And when it is installed in the field, basically you will have a reliable operation of this transformer. Next is a special test. And this usually list of tests comes from the customer, and it's based on the customer wants. So the customer has to list those special tests as part of his specification and send it to the manufacturer for the manufacturer to perform those testing as part of the factory acceptance testing. Next is the list of site acceptance testing. So the site acceptance testing comes into play when the transformer, after completion of the factory acceptance testing, it is shipped to the site upon performing site inspection test, and after installation of the various components of the transformer, this test is performed. And the goal of this testing is to compare the testing results and the parameters with the factory acceptance testing results to make sure that there is no shipping damage, and also to make sure that installation was done correctly. Next is a DGA gassing and fault diagnosis. This is when the transformer, after installation, the transformer is energized and is operating on no load. And oil sample is collected and sent to the lab where DGA and oil quality analysis is performed. And when you identify any severe condition of gassing, then that is when you have to diagnose the fault. And there are parameters, technologies out there that you utilize to diagnose the fault. Next, it's power transformer action. Okay, so as you can see over here, this is a cutaway or a scheme of a single phase idle power transformer. So as you can see over here, we have a primary winding out here. Okay, so the primary winding is equivalent to the high voltage winding of the power transformer. Then on this side is the secondary winding that is equivalent to the low voltage winding of the transformer. This is equivalent to a step up or a step down transformer. Okay, so as you apply voltage to the high voltage side of this transformer, you have a primary current that is going to flow, right? So once you have a primary current that is going to flow, it flows through the core, right? And it excites the core. Once it excites the core, you have a magnetic flux that is going to flow through the core. And this magnetic flux is alternating in nature. It's equivalent to a sinusoidal voltage, right? So as this magnetic flux cuts the secondary winding, it induces that voltage into the secondary winding. And once you connect a load to the secondary side, you can have a secondary current flowing on the secondary side. So in simpler terms, this is a description of the transformer action. Next on the slide is a cutaway section of condensate type of bushing or oil impregnated bushing. As you can see over here, this top section is where the outdoor transmission network get connected. So it's a terminal over here where basically the transmission line can get connected. Then in this section is an oil filled chamber. So as I indicated that this is a condenser bushing, right? It has an oil that basically saturates the paper layers that is wrapped around the conductor, right? So the whole section of this bushing is filled with oil, and as you can see over here, the oil level gauge indicator is shown over here. So that basically you have a port, a visibility port that shows you your oil level, right? And this section is basically a compression spring that keeps a tension on the components below here. In this section, you have a paper layers that are wrapped around the conductor, right? Okay, so like I indicated, those paper layers basically form capacitive layers that grades the electric field. Next, it's a testing tapping point, right? Okay, so inside the bushing, you have a C1 section. So you have capacitive layers that form the C1 section, right? So inside the capacitive layers is an electrode up to the C1 section, and from that electrode to this point is the C2 section. So you utilize this test tapping point for performing testing on the power transformer or the bushing, right? And you can utilize this test tapping point if you want to implement a condition monitoring device, right? It is connected over here. And what are the condition monitoring devices that you can install? You can install condition monitoring devices for measuring the capacitance, the C1 section capacitance, the power factor of the C1 section, the C2 capacitance, and the power factor of the C2 section. Next is the mounting flange, right? Okay, so this is the section that gets connected on top of the transformer or on top of the turret of the transformer. And below that, you have a current transformers. Okay, so this is just an extension below the flange. These are the locations where the CTs are located. The bushing type of CTs are located, where you have the conductor come through the center portion of those current transformer. Okay, on this section, it's a stretch shield, right? Like I indicated, if you have a cable that is connected to the bottom part of this bushing, there's an electric field, and that electric field creates a stress portion in this section of the bushing. So you need a stress shield that is going to grade that electric field. So that is the purpose of this stress shield. Next up is the air breather and the silica gel, right? Okay, so as you can see over here, you'll have a blue type of silica gel. Okay, so this is the old type of silica gel. So currently we don't use this anymore. They are trying to deplete the reserves of this silica gel because of its carcinogen behavior, right? So this is typically installed in a free breathing transformer, open concentrated transformer. This is what allows the transformer to breathe, right? Okay, so during summertime, right? Okay, the transformer picks up load, right? The oil is going to heat up, right, and expand in volume. So when the oil expands in volume, it pushes out air through this silica gel air breather up to the outside atmosphere, right? Okay. Then, on the other hand, if during cold season, the transformer oil contracts in volume. So when the transformer oil contracts in volume, it takes air from the atmosphere, right? It breathes in air. So bringing air goes through this section. This, as you can see over here, you have a pot of oil chamber here, and you have holes around it, right? So the air from the atmosphere goes through this portion and goes through this silica gel, right? And the purpose of the pot of oil is to regulate the amount of air intake, because you don't want a whole volume of air going through this silica gel, right? What is it going to do? It's basically it's going to deplete this silica gel and basically change color from blue to pink within the shortest possible time. And because the goal of this silica gel is for it to last between 6 months to about a year. Okay, so the pot of oil here is what regulates that amount of air intake so that the silica gel can keep longer on this transformer. Next is the marshalling box, right? Okay, or the control uh, cubicle or control box, right? Okay, so this is where you have some of the indicators, winding temperature indicator, oil temperature indicator. You can have or sometimes you can have terminal blocks inside. So this is where all the wiring of all the auxiliary devices, right, can and terminate on a terminal block over here. And from here, it is wired to a local HMI or RTU or to a SCADA system, depending on your communication scheme that you have over here. You can also have these auxiliary devices or indicators, oil temperature indicator, winding temperature indicator, located on the main tank of the power transformer, and the wiring brought into this marshalling box. Inside this marshalling box, you have also relays, cube type relays that control these devices, right, and control the transformer. For instance, you have cube auxiliary cube relays that basically controls the fans of this transformer. You have stage 1 fans, stage 2 fans that are integrated to this oil temperature indicating devices based on set points from the needles of these gauges. Inside this marshalling box are also heaters, right? Okay, so these heaters are the ones that keeps the moisture away from the marshalling box, because you don't want condensation on the terminal blocks of the marshalling box. The goal of the heaters is to keep the condensation away, and because when you have condensation on the terminal blocks, it is going to cause a short and can cause a spurious tripping of the power transformer. Next are standards that you can utilize for the power transformer and its components for testing and for managing the power transformer. Of course. So the first one is IEEE C571290. Okay, so that itself tells you the test code or the tests that can be performed and on a power transformer, distribution type transformer, or regulating transformer. Next is loading of the power transformer. As you know, sometimes the customer or the utility owner wants to overload the transformer. This standard or guide tells you how much you can overload, percentage wise, how much you can overload the transformer, and the duration. Because the goal of overloading the power transformer and the goal of this guide is that you don't want to create hotspots on the paper insulation in the transformer. Because if you overload it beyond the required duration, that is when hotspots can be created on the paper insulation and gassing can be created. And that can lead to deterioration of the paper insulation and also reduction in the operation of the power transformer. Next is IEEE C5793. That is a guide that tells you on how to install the liquid immersed power transformer and the processes that you are supposed to go through. Next is IEEE C5712. This is just a general requirement for distribution type of transformer, power transformer, and regulating type of transformer. So a typical insider that you can get from this standard, it's basically the nameplate, how to interpret the nameplate, and also selection of the impedance based on the kVA or the MVA of the transformer. Next is IEEE C57104. That basically tells you how to interpret the gassing of that is generated in the power transformer. As you can see over here, in this section of the guide, you have different conditions or different stages or different grades. Condition 1 tells you the level of ppm that you are supposed to have for different gases in the transformer: hydrogen, methane, acetylene, ethane, ethylene, carbon dioxide, carbon monoxide. Condition 2, condition 3, condition 4. So condition 3 and condition 4 being the severest, and that requires intervention and action. It also tells you the total combustible gases that you are supposed to have, right? And beyond that range, it tells you to take an action. Next is IEEE 62, basically tells you it's a guide for performing diagnostic field testing. It tells you all the testing parameters that you're supposed to perform on the power transformer and any other electrical apparatus. Next is IEEE C57106. This tells you the testing on acceptance of insulating liquids in power transformer. And C57139 is for dissolved gas analysis of low tap changes. As you know, low tap changes have a different way of analyzing their DGA, and usually it comes from the manufacturer. The manufacturer has to provide you the criteria, and the criteria is usually based on the number of years in operation, right? Or based on the number of operations of the tap changer and the gassing that it has achieved. These are some of the criteria that basically the manufacturer tells you to evaluate to take a course of action. Next is application of a monitoring to liquid immersed power transformer. Okay, so what are the monitoring devices that we can apply to a power transformer? That is, the first one is bushing monitoring. So bushing monitoring, what are we wanting to know? You know, we want to know the C1 capacitance section, C1 of the capacitance of the C1 section, the power factor of the C1 section, the capacitance of the C2 section, and the power factor of the C2 section, the leakage current, and the watts loss of the bushing. We can also have DGA monitoring devices. We can have many of them, depending on the size of your transformer. We have the 2 gas, the 5 gas, the 7 gas, and of later we have the 9 gas. We can also have a monitoring device for the tap changer to monitor the tap changer motor, the current, the voltage, and the torque, and also the contactor wear of the tap changer. Now let's talk about the different type of tests that can be performed during factory acceptance test, or FAT test for short. The first one is a routine test, and the next one is a type test or design test. And like I made mention that design test is when you have a new design of transformer in that family, or you have a transformer that is customary built for the customer. Then that is when you have to perform design tests. Next is a special test, and the special test comes from the customer. The customer has to list the type of testing that needs to be performed on that special test. Next, let's go through the routine test, the list of routine tests that can be performed. The first one is oil breakdown or dielectric breakdown voltage. The dielectric breakdown voltage is a test that measures the withstand of the paper insulation, the mineral oil, to withstand lightning impulse voltages, or switching impulse voltages, or power frequency over voltages, right? Okay, so the list of criteria for this is based on the high voltage of the power transformer, right? Okay, so 69 kV and below has a withstand voltage criteria. Between 69 kV to 280 kV volts, it has a withstand criteria, and above 280 kV volts, the withstand criteria is about 52 kV, right? So the dielectric voltage has to be above 52 kV. It shouldn't be less than 52 kV for a new power transformer. Next is a measurement of moisture, that is water content inside the paper insulation and oil insulation, right? Okay, so similarly, moisture degrades this insulation, oil and paper, right? So You don't want that too much moisture in the oil and the paper. Right? Okay, so below 69 kV voltage has a criteria of moisture that has to be below that. All right, so the difference between moisture and breakdown voltage. So the ppm level of moisture has to be below 22 ppm, and between 69 kV to 280 kV is about 26 ppm, and above 280 kV is about 32 ppm. It has to be below that. Next is tense ratio, right? Okay, so tense ratio, you perform the testing of the tense ratio to make sure that you don't have any broken strands, you don't have any turn-to-turn short, you don't have any open circuits, you don't have any connection problem between the winding leads to the cable, from the cable to bottom connection of the tap changer. You don't have any connection problem in the tap changer, right? So that is when you perform this test, and what you measure is what you compare with what was obtained in the factory. Then again, you don't. It tells us that basically there's no any damage to the transformer during shipping. Right? Next is polarity testing. Polarity testing basically measures the instantaneous of the current flow in the high voltage winding, in the direction of flow of the current, right? For the high voltage and the low voltage. And for the high voltage, it should be into the polarity, and for the low voltage, it should be out of the polarity. Next is the vector group. Okay, so as you can see over here, let's say if you have a DYN1 power transformer. So DYN1 means the high voltage winding is a delta form winding configuration. The low voltage winding is a Y with the neutral grounded. Right? Okay, and the one means the phase shift between the high voltage and the low voltage is 30 degrees. So one is a representative of the clock system, right? So between 12 o'clock and 1 o'clock is 30 degrees, right? So it means that the high voltage winding is leading the low voltage winding by 30 degrees. And the goal of this testing, and basically making sure that the vector group of the transformer is what was designed, right, is to make sure that the transformer can be installed in the parallel configuration in the field, and to mitigate circulating current flow. So you perform this testing and compare it with what was obtained in the factory. And you can also compare it with what is shown on the nameplates. Okay, so as you can see over here, the tense ratio will be different also on different taps, right? If you have a de-energized tap changer, the tense ratios are going to be different. So you perform this testing on each de-energized tap level, and also on a low tap changer level. Okay, so for instance, if you have a transformer with a low tap changer of plus or minus 10%, right? So you perform the test on each tap level that you have. Let's say if you have a transformer that have a tap changing of plus or minus 16.5%, you do that testing on each tap that you have. Next is winding resistance testing, right? Okay, so the winding resistance testing measures and tells us if there are open circuits, if you have turn to turn shorts, broken strands, if you have any connection problem between the winding leads and the cable connection to the bottom of the bushing, or you have a tap changer problem, right? Okay, so you perform the testing for each phase, right, and compare the testing between phases. It shouldn't be more than 2 to 4% of the average of the winding resistance testing. Then again, the goal is to perform the testing and the measured winding resistance, compare it with what was obtained in the factory, and make sure that there's no significant change in the winding resistance. The winding resistance also gives us an indication to calculate the copper or the load loss, and that is used in performing the temperature rise tests of the transformer. Next is a measurement of the copper loss, right? Okay, so once you're able to measure the winding resistance, right, you use it to calculate the load loss or the copper loss, because I squared R, basically the current that is flowing, the square of that, and the resistance, the measured resistance. And we utilize that to perform the impedance, right, test. The impedance test basically tells us basically the arrangement of the active component inside the transformer, the arrangement of the insulation, and the path that the leakage flux flows, right? Okay, so during shipping from the factory after factory acceptance testing to the site where the transformer is going to be installed, the transformer can get damaged, right? Or the active component can get shifted when the transformer, let's say, falls down. Okay, so the goal is to perform this impedance testing and compare it with the testing results that was obtained in the factory. And there should not be any change greater than plus or minus 7.5% for a new transformer. If there's any significant change, if you compare the results, that tells you that there is an imminent shift in the active component, and you have to do another testing, that is the SFRA, frequency response analysis testing, to compare the fingerprint of the active component of the transformer. So these test results will give you an indication of an internal damage inside the transformer. Okay, so for the polarity and the vector configuration, I think I've discussed about it on item 3 of this presentation. Next is excitation current, right? Core loss and no load loss. Okay, so excitation current gives us an indication of a core damage, right? And also a strand damage or a turn-to-turn short inside the transformer. Okay, so you perform that testing to calculate the core loss. You utilize the core loss in performing the temperature rise test. Both the core loss and the load loss gives us the total loss, and that is what you use to perform the temperature rise test, to make sure that the rise above temperature for the oil meets the design criteria, and the rise above ambient for the winding meets the design criteria. So what you do is that you compare the excitation current that is flowing in the external lengths, phase A and phase C, with the phase B length of the core. And the milliamps, the excitation current milliamps that is flowing in phase A and phase C should be the same. And that one flowing in phase B should be different from what is flowing in phase A and phase C. Next is insulation resistance testing. Insulation resistance testing tells us the level, or gives us an indication of the level of moisture intrusion onto the insulation, and also the level of contamination, the level of oxidation of the oil, right? Okay, so in performing the insulation resistance, you perform it at 0 minute, 15 minutes, and 1 minute. Then after that, an increment of 1 minute up to the 10th minute. At the 10th minute, you utilize the 10th minute and the 1 minute to perform to calculate the polarization index. The polarization index also gives us the level of contamination that we have and the moisture intrusion into the insulation resistance. Okay, so for a new transformer, we are expecting a polarization index greater than 2.0. Anything below that is unacceptable for a new transformer. However, for a service age transformer, we are expecting a polarization index of 1.5 and above. Anything below 1.5 and below falls short of that and requires investigation, right? Okay, so the insulation resistance value too, we are expecting for a new transformer, we're expecting a gigaohm range. And for a service age transformer, we're expecting about 100 mega ohms. Next is induced voltage, right? Okay, so we perform these to check the major insulation arrangement and the quality of the major insulation. Okay, so the major insulation of the active component of high voltage to ground, low voltage to ground, and in between the high voltage to the low voltage to withstand the operating voltage and also power frequency over voltage condition. And during that time, at the end of the test, that's when we measure the partial discharge activity, to determine if the insulation integrity is intact and there are no voids inside the insulation. Next is power factor test. Okay, so power factor test basically tells us the level of contamination inside the oil and the paper insulation. And the acceptance criteria for a new transformer is plus or minus 0.5%. And anything greater than 0.5% and above for a new transformer is unacceptable. However, for a service age transformer, you want something between 0.5% to 1%. Anything greater than 1% is unacceptable. Excuse me. Next test is applied potential test. Okay, so this test is also called a dielectric storm test or separate source testing for the high voltage side and for the low voltage side. Okay, so this testing is performed and it's a 1-minute test. It's to make sure that the insulation can withstand steady state operating conditions and also power frequency operating condition, power frequency over voltage conditions. Next is the functional testing of all the auxiliary devices in our session. As you know, the auxiliary devices that we have are pressure relief devices, winding temperature indicator or winding temperature devices, oil temperature indicator or devices, solid pressure relays, oil level gauge, right? So you perform the functional testing of all these auxiliary devices, check all the alarm and trip points. So basically, it's integration into the tripping points up to the DCS or the SCADA system. Next is the ratio and polarity of the current transformer, right? As I indicated, you have CTs that are located on the below the flange of the bushing, right? So you perform testing of the ratio and the polarity of the CT, right? And the polarity is very important, especially to check the integrity of the CT in terms of the direction of the current flow, especially the differential protection for the power transformer. Another testing that you perform is insulation resistance on control circuits. So this testing is performed at 250 volts. That is a very low voltage. Okay, so next we'll talk about the design test. And design test, like I indicated, design test is when you have a new family of transformer that is going to be manufactured, that has been designed and it's going to be manufactured. So you have to prove beyond reasonable doubt that the design is going to work as it is supposed to be, right, per design. And if the transformer is installed in the field, it is going to basically operate reliably. Okay, so these are the list of design tests that can be performed. Okay, so the first one is a turns ratio. Okay, so the turns ratio test or the voltage ratio test, right, is performed to identify broken strands in each turn, broken turn-to-turn shorts, then broken connections between the winding lead and the cable connection, broken connections between the cable connections and the bottom connection of the bushing, broken connections of the tap changer leads. Okay, so the acceptance criteria is plus or minus 0.5%. You compare the measured results with this acceptance criteria, with the nameplate, what is on the nameplate, and make sure that it meets the acceptance criteria. Next is winding resistance. What does winding resistance tell us? Winding resistance basically gives us an indication of broken strands, right, and also open circuits, and also broken connections between the winding lead and uh, the cable connections, and also from the cable connection to the bottom part of the bushing, and also tap changer problems, connection between the tap leads and the tap changer. Okay. So during this testing, current is injected, and when the current is injected, the voltage that is measured from there, the winding resistance is determined, and it is corrected to about 80 degrees Celsius or 90 degrees Celsius. We also utilize this results to determine the copper loss, I square R, and we utilize this load loss or copper loss to as part of the temperature rise test. Next test is a measurement of the copper loss, right? Okay, so once we're able to determine the winding resistance, and during the short circuit test, right, low loss test, where we short circuit the low voltage side, right, and we apply 5 to 15% or 5 to 10% of the rated high voltage voltage until we achieve a rated current flowing through the transformer. So from there we measure the copper loss using a watt meter that is located on the high voltage side, and from there we can calculate the impedance voltage. We also utilize this load loss to perform the temperature rise test. Next is polarity and vector configuration. Okay, so polarity basically tells us the direction of current flow, instantaneous current flow that is flowing into the high voltage winding and the low voltage winding. So for the high voltage winding, the direction of current flow is into the polarity, and for the low voltage winding, the direction of current flow is out of the polarity, right? Okay, so this measurement or test tells us that we have the right polarity of the winding arrangement. And vector configuration, right, like I indicated on the previous slide, if you have that tells us the phase shifts between the high voltage and the low voltage. Okay, so for example, if you have a DYN1 transformer with a vector configuration, so the high voltage is a delta 1 configuration, right? And the low voltage winding is a Y with a neutral grounded. So the neutral can be solidly grounded, or the neutral can be resistance grounded. And the 1 tells us the phase shift between the high voltage side and the low voltage side. So the 1 is just like the clock system of the regular clock that we have. So between 12 o'clock and 1 o'clock is 30 degrees, right? And the total of the whole clock is 360 degrees. So that angle between 12 o'clock and 1 is 30 degrees. So the 1 itself tells us the high voltage winding leads the low voltage by 30 degrees. Okay, so this vector configuration phase shift test helps us to basically validate the integrity of utilizing this power transformer in the parallel configuration in the field to mitigate our circulation current flow. Next test is the excitation current test. Okay, so the goal of this testing is to also called open circuit test. Okay, so the goal of this testing is to basically measure the amount of excitation current that is flowing through the magnetization branch of the transformer. So based on that, we determine the core loss test. Okay, so based on the amount of excitation current that is flowing that we measure and the resistance of the core has an inductance and also has a resistance. So the inductance and the resistance are in parallel configuration, and the amount of current that flows into the magnetization branch is split with a part flowing through the resistance part and another part flowing through the inductance part. So from there we determine the core loss, and that also is the same as your no load loss. So the combination of the no load loss and the load loss gives us the total loss. So this is amount of wattage that we utilize during the temperature rise test. Next test is the temperature rise test, right? Okay, so the goal of temperature rise test is to make sure that the transformer is energized and basically during stabilization um, for about 25 or 4 hours or more. The temperature rise above ambient for the oil meets design criteria. Let's say for a 65 degrees Celsius oil temperature rise, the measured temperature rise during stabilization of the transformer run, it's below 65 degrees. Likewise, for a winding temperature rise, let's say for a 65 degrees C temperature rise design of a power transformer, what we measure during stabilization of the temperature rise test is below 65 degrees Celsius. Next, impedance voltage or low loss test. So that is similar to item 3, copper loss, impedance, and low loss test. Next is vacuum test. Okay, so vacuum test, we perform this test to measure leaks on the power transformer. As you know, the transformer main tank, right, is welded, and these days technology has improved that basically the transformer tank is not welded. Basically, it comes in various sections and it is bolted, right? Okay, so the vacuum test is performed to make sure that there are no leaks inside the main tank. And also, during filling of the transformer with oil before energization, that test that is done under vacuum to make sure that there are no gassing or bubbles that is going to form. Because those gassing and bubbles, when they form, is going to deteriorate the paper and the oil insulation, and basically compromise the reliability of the oil and the paper when the transformer is in service. Next is capacitance in turn delta testing. Okay, so as you know, the active component of the transformer is made up of insulations, right? You have the high voltage insulation, the low voltage insulation, and insulation between the high voltage and the low voltage, right? So the paper insulation, the oil insulation, the insulation between turns, right, forms a capacitance. So you have a high voltage capacitance to ground insulation, low voltage capacitance to ground. Capacitance formed between the high voltage and the low voltage. All these capacitance are formed because of the insulation arrangement, the paper and the oil. Right? So you measure this capacitance to indicate the winding arrangement. So that becomes like a fingerprint, a baseline for this transformer throughout the whole operating history of the transformer. So in the future, let's say during site acceptance testing, or in the future during the operation of the transformer, when a routine test is performed, you compare this capacitance testing with the factory acceptance testing to identify any internal active component shift of the transformer or the winding arrangement shifts. Next is the turn delta, the power factor. Okay, so that testing tells us the integrity of the insulation, the paper and the oil insulation of the transformer, the contamination level, the moisture intrusion, the oxidation content of the insulation. The capacitance testing also tells us the deterioration of the paper insulation. So as this paper insulation gets deteriorated, definitely, once the capacitance is formed with this paper and the oil, as it deteriorates, definitely the capacitance is going to change. Right? So that itself, the testing itself gives us an indication of the capacitance change. So for a new transformer, we are expecting that in the future, after the design test is performed in the factory, right? And in the future, if you perform the site acceptance testing or the routine test, the change in capacitance shouldn't be more than plus or minus 5% for a new transformer. For a service age, more than 10 years, it should be more than 10%. Anything greater than 10% gives us concern for us to investigate and identify perform other testing, like impedance testing, SFRA testing, to identify the need to perform an internal inspection of the active component of the transformer. Next testing is a special test. Okay, so like I indicated, special test comes from the customer. The customer has to basically request that testing. Okay, so that testing is indicated as part of the customer's specification, transformer specification, that is going to be sent to their manufacturer, being ABB, Siemens, GE. Okay, so the first special test that we have on this list is zero sequence impedance. Okay, so why the need for zero sequence impedance? Zero sequence impedance is requested when basically the protective relay engineer needs to use that impedance to perform line to ground, or to determine the line to ground fault currents and double line to ground fault current. Okay, so as you know, the positive sequence current is equal to V over ZO plus Z1 plus Z2, right? Okay, so the ZO part is the zero sequence impedance. Then the Z1 is the positive sequence impedance. Then the Z2 is the negative sequence impedance. Then plus 3ZN. If you have the transformer connected to any neutral ground resistance, that is the 3ZN part of the bottom part of this equation. Okay, so the Z1 is the nameplate impedance that you determined in the previous slide during the routine and the design test that you perform. So the negative sequence impedance testing, more often than not, the negative sequence and the positive sequence are quite the same, right? Okay, so the Z1 is equal to the Z2, okay, for most of these core formed transformers. But the ZO, then the zero sequence impedance, has to be determined. Okay, so we perform this special test to determine the zero sequence impedance. Okay. So next is the harmonic content of the no load current, right? Okay, so as you know, if a power transformer has a differential protection, right? Okay, so as part of the differential protection settings, the goal is during energization of the transformer, there's something they call inrush current. Okay, so that inrush current is rich with second and fourth harmonics, and third and fifth harmonics. It's very rich with that. Has a high content of that. Okay, so during energization of the transformer, the inrush, magnetic inrush, basically, the transformer can misinterpret it as a fault, right? So we need to have a scheme that would differentiate this energization scheme with actual faults, right? So actual fault, the second and the fourth harmonic is very low. Okay, so we can utilize that high harmonic content excuse me, during of this harmonic content to distinguish between magnetization inrush and an actual fault condition, right? So we utilize the second harmonic and the fourth harmonic that is measured to accurately set this relay, right, to mitigate, to prevent spurious inadvertent trip of the differential protection during energization of the transformer. Then again, for overexcitation condition during load rejection, right, that is when you can have overexcitation and high flux density that can saturate the core, right? So the third and the fifth harmonic can increase during that time. So that is when we measure this harmonic component to be able to set the third and the fifth harmonic and to inhibit the transformer during the no load energization, and that is a magnetic inrush. Yeah, because when the transformer is not connected to any load, definitely there's going to be over excitation. and the third and the fifth harmonic is going to be high, right? So you have to inhibit that, set that, inhibit that, and so that the transformer wouldn't think that you have a load rejection condition, or you have an overextension condition. Next is a functional test of the pressure relief device. Okay, so the pressure relief device is located on top of the transformer. Okay, so that is the last sort of protection for the transformer. After your differential protection fails, your sudden pressure relief device protection fails, right? You have a backup protection of 50 instantaneous fault protection and time over current protection on the high voltage side. If that protection also fails, right? That is when the pressure relief device comes into play. So at that time, the fault has evolved and has grown. So you have a lot of pressure built up in that transformer. So the goal of this device is basically to expunge, open up and expunge all the pressure that is inside the tank. Okay, so you perform a functional test of this relief device. Then the buckles too, it's utilized in free breathing transformers, open conservative tank transformers. So the buckles relay or device is located in between the conservative tank and the top of the main tank. There's a piping called downcoming piping that is sloped at an angle of about 7 to 8 degrees. So in the middle of that is the buckles device. And the goal of the buckles device, the buckles relay or device performs three functions. The first one is basically it identifies when the transformer has a low oil level, right? Remember, the conservative tank is the one that basically replenishes the oil in the main tank. If the oil in the main tank leaks, the conservative tank is the one that basically replenishes that oil. So as the conservative tank is replenishing that oil and the conservative tank, becomes empty, definitely a vacuum is going to be created. And at that time, the conservative tank, the buckles relay is going to identify that condition and trip the transformer. The second function of the buckles device is an incipient fault. An upcoming fault, a gradually developing fault. Let's say from a 10 to 10 shorts, broken strands, broken connections. So if you have that condition inside the main tank, what happens? You will have a gassing, acetylene gassing for that instance will start developing, right? So this gassing, basically, they are lighter, so they rise up and basically collect inside a chamber inside in the buckles devices. So gradually these buckles devices build up the volume of inside the buckles devices. Then the weight of that volume basically impinges on a micro switch, basically that activates and basically trips on that condition. No, actually, I take it back. It allows for investigation to be done to find out. It doesn't trip automatically. Next function of the buckles is through fault. As you know, if you have a through fault, let's say on the low voltage side of the transformer, then you have basically a fault that is going to flow from the source through the high side, through the internal active component of the transformer. So basically, the high fault current is going to cause high electromagnetic forces, right? That is going to develop, and that is going to shake the active component of the transformer. So the shaking of the active component, the core and coil, is going to cause a pressure wave, a high pressure wave. That is going to cause this oil to flow backwards on towards the conservative tank, right? So that flowing is going to flow, hit a valve that is below the buckles device. So it's going to hit that, it's a flat shape valve. So that itself is going to trip the transformer. It's going to activate a micro switch and trip the transformer. So those are the conditions that trip the transformer based on the operation of the buckles relay. All the conditions are alarm. Next is the sudden pressure relief device. The sudden pressure relief device on most transformers are located on the corners of the main tank, right? You will see about one or two of them, you know. And in the nuclear industry, we used to have more than one, you know. That is based on basically reliability purposes. Now, because the sudden pressure relief devices are prone to nuisance trip. So, in the nuclear industry, to avoid those nuisance trip, what they have is two pressure relief devices that are located on each corner. So all two have to see the pressure wave that is formed from the electromagnetic force that is formed from the high current, short circuit current that flows through. The high short circuit current forms a pressure wave, and basically it impinges on the bellows of the sudden pressure relief device. So all two have to see the fault and fault before the sudden pressure relay will activate. And most often than not, the sudden pressure relay device is integrated to an auxiliary device, 64X. And from the 64X, it goes to a lockout relay. And from the lockout relay, it trips the trip call of the main breaker. So you perform functional tests of these based on the customer wants, and basically to identify the functionality and validate the functionality of these auxiliary devices as they are going to go into service. Next is acoustic sound level. Acoustic sound level comes into play when the customer is going to install the transformer in an area inside the city based on the city ordinance, right? Okay, so the city requires the transformer to emanate a certain required sound level. Okay, so let's talk about how does this transformer emanate, produce sound level. The first one comes from the core. The core is made up of laminations, right? Okay, so when the transformer is energized, right, and then you have a flux, magnetic flux flowing through, traversing the path of the core, what it does is it causes something they call magnetostriction. That is chattering of the laminations of the core. So that chattering creates that humming sound. Another source of current is eddy and hysteresis current that is flowing through the winding of the transformer. Another source of sound is leakage flux that impinges on the tank, the walls of the tank, that creates a sound level. Another source of sound is from the cooling fans. The cooling fans. So the cooling fans, as it's on, you have a different stages, stage 1, stage 2. Okay, so that itself, when it is operating, creates another source of sound level. So all these sources are the total combination of sound level. So testing has to be done. So testing is done on no load, and testing is done with load. And the sound level is measured at different corners, at different heights, to determine the total acoustic sound level meets the criteria specified by this customer. Next, the power taking, the power that is taken by the fans and the pumps, right? As you know, the voltage that is going to be fed to these fans and the pumps comes from an auxiliary source. That is most often than not, it comes from a motor control center, right? Okay, so as part of the load list for the motor control center, you want to identify and size the breakers that are going to be on these motor control centers. So you identify the power, and from there you can perform the sizing of the breakers of this motor control center. Next is site acceptance testing. Okay, so once you have completed all the factory acceptance testing, that is the routine testing, the design testing, right? Then the next testing that you need to perform once the transformer is shipped from the factory to the site is site acceptance testing. Okay, so site acceptance testing, what are the testing that is performed? Okay, first one is when the transformer is shipped from the factory, basically all the auxiliary components are disassembled and packaged nicely. And once they reach, and depending on the size of the transformer, usually transformers that are greater than 20 tons, right? That is 20,000 pounds or so, right? The manufacturer attaches an impact recorder. And what the impact recorder does is it basically measures damage on the transformer. If there's any damage due to transportation, as you know that during transportation, the transformer can get damaged, and so the impact recorder measures these G forces that comes into play. And the forces are axial, radial, and vertical forces. Yeah, so all these forces are summed up in basically the impact recorder. So when the transformer arrives, one of the things that you are supposed to do as the field engineer or the discipline engineer is in coordination with your project managers is to remove the impact recorder and send it back to the manufacturer for them to analyze if there was any impact, heavy impact and damage to suspected damage to the transformer. The next thing you want to do is inspect all the components that were removed before shipping. As you know, like I indicated, when those components are removed, the transformer oil is also drained, and the transformer is filled with air. Okay, so one of the inspections you want to do is dew point testing due to the transformer being filled with air to make sure that there's no heavy contamination inside or condensation inside the transformer. So once you perform all the inspection of the components, that is the radiator, all the gauges, oil temperature indication, winding temperature indication, and sometimes the sounding pressure relay device is kept intact. Rather, the control cabinet, is basically boxed. They have a protective layer that is boxed around it to make sure that it doesn't get damaged. Next is the oil temperature indicator. Site acceptance testing is performed on that, and the winding temperature indicator, the oil level gauge, all these gauges after installation. After installation, one of the first things that is also done is the foundation. Remember the foundation of the transformer. The foundation is put into place during the material takeoff. That is when you work with the structural engineer, and also based on the weight of the transformer during the design phase, that information is given to the structural engineer, where the foundation is designed to handle the weight of the transformer. Right. Okay. So it is at this time that basically the structural engineer also comes around to make sure that there is no damage during installation, installation of the transformer. So the next check that you want to do is check out the air breather, the silica gel. Make sure that it is filled with the right required silica gel and the right color. And next is the cooling fans. Basically, you perform a test of the cooling fans to see the direction of rotation, right? Okay, and also to measure the incoming, current and the voltage that these cooling fans are consuming. Next is the oil pumps. Also, you check if you have an oil pump. Usually they use the oil pumps to pump fluid into the winding to remove heat from the winding faster. Next is a functional test of the sounding pressure relay, and basically this testing is done with the integration of the sounding pressure relay with its auxiliary relay 63X and the lockout relay to the trip core. Similarly, for the pressure relief devices, most often than not, the pressure relief device is used for alarm purposes. So you also want to check out the alarm of that. The bookhouse device is usually used for alarm and trip. So you also want to check, functionally test it, and test the integration of the alarm and the trip point. Next is insulation resistance and polarization index test. As you know, like I indicated, you want to check to make sure there's no internal contamination, because the transformer is filled with air, right? Okay, so you want to make sure that there's no moisture ingress during transportation, and also determination of the polarization index. Next is operational check of the OLTC. Next is capacitance testing and tan delta. Like I indicated, that capacitance testing tells you the arrangement of the major insulations of the internal to the transformer, the high voltage to ground, the low voltage to ground, and in between the high voltage to the low voltage based on the capacitor. So you perform that testing and compare it with the nameplate data and the factory acceptance testing. Similarly, the tan delta measures the level of contamination and moisture ingress. You perform that testing and compare it with the nameplate data and any factory acceptance testing that was performed. Next is the turns ratio. Similarly, you perform that testing and make sure that it doesn't deviate by plus or minus 0.5%, and compare it with the nameplate data and the factory acceptance testing. And just to add a little bit to the tan delta, tan delta, when you do the testing, you compare it with acceptance criteria of 0.5%, right? It shouldn't be more than 0.5%, and you compare that testing results with the factory acceptance testing result. Next is the vector growth and the polarity and the winding resistance. When you perform that testing, you make sure that in between the phases, phase A, phase B, phase C, it doesn't deviate by 2 to 5%. Magnetic balance, that's also one of the important, basically it measures the balance nature of the active component, the active core of the transformer. Make sure that the flux path is balanced. Next is vibration. When the transformer is energized, right? Okay, so you want to measure the vibration. As you know, the transformer is sitting on a foundation, right? Okay, and the vibration is measured to make sure that the transformer, when it's in operation, the vibration that it emanates wouldn't destroy the foundation. Next is sweep frequency response analysis. That is one of the most important, called fingerprint testing. So, during factory acceptance testing, sweep frequency response analysis testing is performed, right? So, you perform the testing again to identify any shipping damage, right, on transit of the transformer to the site, right? Okay, so that testing, in addition to the impedance testing, will give you an indication of any internal damage of the transformer during shipping. So the plot that you achieve, you compare it with what is received in the factory. Next is the extension current. That itself tells you of any internal shorts in the winding, the strands, broken connections, and also any damage to the active component of the transformer. That is the core, any insulation damage that is causing basically an internal short circuit. Next is the short circuit impedance. Like I indicated, short circuit tells you an internal arrangement of the insulation system, an active component, and the flow of leakage flux through this arrangement. So any deviation tells you that the active component has shifted. Next presentation, and basically it's a DGA fault diagnosis. Okay, so as you energize the transformer, and the transformer is soaked, let's say for 24 hours or more, and on no load, then that's when you collect an oil sample and send it to the lab, right, for oil quality analysis to be performed and chemical composition and dissolved gas analysis to be performed, right? So once you identify severe gassing, combustible gassing condition, that is when you move to the next step or level to utilize any of these schemes to identify a problem with your transformer, right? So the first one is key gas method. That basically gives you an indication of the different relationship between the combustible gases. The Duval's triangle, we have a Duval 1, Duval 5. So utilize this basically will give you an indication of the type of fault that you have. Next is the Dunning-Berg method and the Rogers ratio. So next is the type of testing that is going to be performed for oil quality and DGA. Okay, so the first one is moisture, right? Okay, so moisture intrusion basically degrades the paper in the oil, right? Okay, so the goal is to minimize and mitigate the amount of moisture. And so that is why during manufacturing, the transformer insulation system is processed. The paper is processed thoroughly, and basically it goes through different um, drying processes to remove the moisture, keeping the moisture to 0.5%, right? Okay, so you perform the moisture level ppm, and you basically compare it with an acceptance criteria. Next is dielectric breakdown voltage. Okay, so that is the testing that basically tells you the withstand of the oil to be able to withstand lightning impulse voltage, switching impulse voltage, and power frequency over voltage conditions. Next is interfacial tension, right? Okay, so as your transformer oil oxidizes, forms oxidative compounds, contamination, then your interface of the oil basically decreases, and basically the transformer ability to perform its functions also decreases. Next is acidity. So as your transformer paper, thermally upgraded paper, degrades, right? It forms oxidative compounds, and from oxidative compounds, it forms as acids. So you measure these acids to determine the level and integrity of the oil. Next is furan compounds. Okay, so as you can see, like I indicated, the transformer has a lot of paper insulation, right? You have paper, thermally upgraded paper wrapped on the conductor, right? You have compression rings that is made from high density wood, right? You have spaces. You have cylinders. They're all made up of corrugated woods, right? High density woods. So all these papers, as they degrade, basically, they form these oxidative furan compounds that basically becomes part of the oil. So that is a marker for you to, um, when you identify these components based on the level, is a marker for deterioration of the paper insulation. Next is power factor testing, and basically that tells you the level of contamination that is in the transformer for the oil and the paper insulation. Next is the DGA gassing. You have a hydrogen. Hydrogen basically manifests itself based on a partial discharge activity in the paper insulation, right? So if you have an insulation, paper insulation that basically wasn't dried properly, right? The water content was very high, and voids were formed in the paper insulation. Then basically it's going to lead to a PD activity, tracking activity that is going to create a hydrogen. Next is the carbon monoxide. Carbon monoxide comes into play when you have a high heating of the paper in the proximity, close proximity of oil. So that is more localized, and a typical example is hotspots. If you have a hotspot and a heating of the paper, and you have oil that is flowing around the hotspot area, then that is when carbon monoxide will start basically being created. Next is carbon dioxide. Carbon dioxide comes into play during the degradation of the paper insulation. As you know, paper is made up of cellulosic compounds, carboxylic compounds, right? So as they degrade, right, in the presence of oxygen, they basically the oxidative compounds they form carbon dioxide. But on the other hand, you can also have an intrusion of carbon dioxide from the atmosphere into the transformer. So basically, these are some of the things that you have to investigate. If you have high CO2 that is being measured from the oil, there are other testing methods that you can do to identify, to make sure that, and a typical example is your furan compounds testing. That is an indirect method of determining the degree of polymerization, degradation of your paper insulation. For a typical transformer, degree of a new transformer, a degree of polymerization is about 1,200. So as the transformer operates, as it goes into service operation for a longer time, then the degree of polymerization starts decreasing. So An acceptable degree of polymerization is between 800 to 1200. Anything below that is unacceptable for you to put in intervention measures to plan for the transformer to be rewound, right? And if you measure furan compound that is giving you a degree of polymerization of 200, then that is a cause for concern for you to take the transformer out immediately, out of service immediately. Right? Okay, so methane compounds basically tells you basically heating of the paper insulation. Then ethane is basically liquid flux that is flowing through unwanted parts and basically causing heating. Same applies to ethylene. Acetylene is basically broken strands, heating, turn shorts, broken connections. Basically, that tells you that basically you have a broken connection problem that is creating those gassing for you to investigate.